So today we'll see about the SJ components. So whenever user tries to connect to the database, there will be LSNR process, and it creates a dedicated server process. And once the dedicated server process is created, a connection is established between the user and the dedicated server process, and all the communications go through the memory. Now we will see the SGA component. So SGA is actually divided into two parts. One is fixed global area, and the second component is variable global area. Fixed global area and variable global area. These are the two components of SGA. So the fixed global area is nothing but it's like a kernel of the operating system. So if you take the kernel of Linux operating system, first it will have the basic subroutines which are required in order to start or stop the rest of the services, such that users can do all the operations. In the similar way, even in SGA, we will have a fixed SGA component which will have the basic subroutines that will build rest of the SGA. So it is similar to the kernel of the operating system. And fixed global area occupies very small amount of space in the SGA. So it will probably around 4 MB, maybe less than that. And the rest of the SGA will be variable global area. Now the variable global area is divided into three main components. This is variable global area, and this is divided into three main components. One is database buffer cache. Second one is redo log buffer or log buffer. Log buffer. And the third component is shade pool. Shade pool. And this it is a log buffer. So first we will see what is a database buffer cache. So whenever user tries to submit any request to the database, so the request may be select, insert, update or delete. So whenever user is trying to query the database, say for example select star from EMP. So in order to get the faster retrieval, first whenever you issue this command, server process which is running on the server where the database resides, it will check whether the requested table or requested object is present in SGA or not. The SGA component which it looks into for that table is the database buffer cache. So whenever server process gets the table from data files and place it into the memory, it will place into database buffer cache component. So database buffer cache component is the memory where the Oracle objects resides. And for the first time, if the user is performing select star from EMP, and if the object is not present in the database buffer cache. As I said, whenever user performs any request, dedicated server on behalf of the user will search for that object whether it is present in the database buffer cache or not. So as this is the first time the object is being referenced, the object is not present in the memory. So as a result, server process again. This is the database and the physical files are stored in this storage and the objects are also present in these physical files. So the dedicated server process, as the EMP table is not present in the memory, it will get the table from the physical storage and it will place it into the database buffer cache. So the table is stored in the database buffer cache. So after that, shared process will take the component from the memory or the object from the memory and it will give it back to the user. So why we require the objects to be stored in the database buffer cache? So for the faster retrieval. Because for the first time, yes, the access retrieval will be slower because this is the first time the object being referenced. But the subsequent access, whenever the other users are trying to access the same object, instead of accessing the physical storage, it will access the memory and it will give the object back to the user. So as a result, I mean like the subsequent access will access the memory for the objects, the faster the retrieval will be faster. So in order to reduce the physical input outputs, so whenever we are accessing hard disk to get the objects, those are called as physical input outputs, and the physical input outputs are very costly because I mean like it takes a lot of time to fetch the information compared to memory logical input output. Logical input output means accessing the memory component. So in order to reduce the physical input output, the objects being referenced are first stored in the component of the SGA, which is called as a database buffer cache. So database buffer cache is mainly used to reduce the physical input outputs. I'm just taking the three main components of SGA. As I said, shade pool. So within this database buffer cache, as I said, this is the memory component which stores the actual objects in the memory. Now, if you go deeper into this database buffer cache, it is divided into components called as buffers. For example, the size of total SGA is 500 MB. Out of this, 300 MB is allocated for the database buffer cache, 300. 195 is allocated for shade pool, and 5 MB is allocated for read log buffer. Okay. Now, out of this 300 memory, it will be divided into buffers, and this buffer size will typically be equal to database block size. So this buffer size will be typically equal to database block size. So first we will see what is a database block. So for example, in Windows, whenever you have a pen drive, whenever you are formatting that pen drive, for example, you have a 4 GB pen drive, and when you want to format this pen drive, first you will select the type of file system you want, whether you want NTFS or FAT file system on your 4 GB pen drive. After that, if you actually see below the file system type, there will be a block size. So for example, this 4 GB and the block size is 256 KB. That means whenever Windows formatting this pen drive in NTFS file system, it actually divides the 4 GB into blocks of 256 KB. In a similar way, even in Oracle database, we will have a block size. So that means if you are creating a 5 GB of physical file, so actually there are physical components of database, and one of the physical component of the database is data files. So whenever you are creating a 3 GB data file, it will be divided into blocks, and that block size will be equal to the database block size. And the database block size we will be specifying whenever we are creating a database. So while creating the database, we will select the block size. And once we select that block size, for example, if it is 8 KB, then if you are creating a 3 GB data file inside the database, this 3 GB will be allocated in terms of 8 KB blocks. In a similar way, whatever the 300 MB is allocated for the database buffer cache, it will be divided into buffers, and that buffer size will be equal to database block size. So this 300 MB will be in chunks of 8 KB blocks. And each block is called as a buffer. In the physical storage, it is called as a data block. In the logical storage, it is called as a buffer. And that is the reason why it is called as a database buffer, data buffer cache. It is storing the data, and thus it stores it in the buffers. And as it is a cache, that means it is, it's a memory component. Now, in these buffers, a buffer can be of free buffer, dirty buffer, clean buffer, and pin buffer. So a buffer in the buffer cache can be of either these four kinds. It can be free buffer, dirty buffer, clean buffer, or a pin buffer. So whenever an SGA is allocated for the Oracle database, for example, this 300 MB is allocated for the database buffer cache. So initially, when this SGA is allocated, there are no objects present in this buffer cache. As a result, all the buffers will be called as free buffers because those buffers doesn't hold any data. So those are called as a free buffers. So free buffers are the buffers which are not used yet. And coming to the dirty buffers. So the second type of buffers are called as dirty buffers. Now, when user comes into the database and he issues insert statement, or for example update statement. So he is issuing an update statement, update EMP set salary equal to 300 or 3000, where EMP number or department number equal to 10. So this will update the salary of all the employees who are located in department number 10 to 3000, correct? So whenever this statement is issued, first dedicated server process will check EMP table is present in the memory or not. So if the EMP table is not present in the memory, as I said, the server process will look into the physical files, it will get that object and it will store it into the memory. Once it is stored, this update statement will be performed against that object which is present in the memory. So it will update the blocks which are corresponding to the employees whose department number is 10. So for example, these are the blocks which constitute for EMP table. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the total 12 buffers consumes are the 12 buffers are used to store the EMP table. Now, out of these 12 buffers, say for example the 4 buffers are corresponding to the department number 10 employees. So these 4 buffers will hold the rows which are corresponding to the department number 10 employees. Now, it has to update the salary to 3000. Whatever the salary may be, whatever the before salary may be, it needs to update the current salary to 3000. So that means it will update these 4 buffers. Now, whatever the information present in the memory corresponding to the department number 10 is not present in the physical files yet. These are the physical storage, and this is the data file in which EMP table is present. Now, the department number salary is 3000, but the 3000 is set to the rows which are present in the buffer cache. Those are not updated yet in the physical storage. The physical files are not updated yet. So that means whenever the information present in the buffers doesn't match with the content of the data files, those buffers are called as dirty buffers. If you remember, I said whenever the user is trying to update or insert that statement, whenever he issues that statement, after processing that statement, the content from the memory will not be written back to the physical storage. For each and every statement, the background process will not write the content from memory to the data files. If it writes, it will consume lot of physical input output. The main concept of this memory will be to reduce the physical input output. So that is the reason why even though the user issued this update statement, whatever the information is updated, it will be stored in the memory itself. It will not be updated into the database yet. So those buffers are called as dirty buffers. Okay. And next, coming to the clean buffers, whatever the content present in the buffers is equal to the content which is present in the data files. So all the rows in the data files and all the rows in the buffer cache matches. Then those buffers are called as clean buffers. Next, pin buffers are the buffers which are in use. So if you take these 12 buffers, all these 12 buffers are holding EMP table. That means those are called as pinned buffers. Any questions?
No, morning. I mean, it's clear.
Now we'll see the second component, which is shade pool. Actually, shade pool is divided again into two components. Shade pool itself has two components. One component is called as dictionary cache, and the second component is called as library cache. first we'll see about the library cache component. So we'll take the same example. When the user is trying to issue the statement, update statement, first whenever the user tries to submit a query to the dedicated server process, first Oracle will check whether all the keywords are spelled properly or not. So it actually performs a syntax check and also semantics check. So the syntax check is nothing but it will check whether all the keywords are spelled properly and the statement is framed properly or not. So once it performs the syntax check, then it will check whether the EMP table is present or not, and also it will convert the statement into meaning. Okay, this is update statement. Now this SQL statement will be converted into a format called as relational algebraic expression. So whatever the commands you're issuing, it internally converts the statement into a relational algebraic expressions. And after performing the syntax and semantics, the total code will be called as a compiled version of the code, compiled version of the command. And that compiled version of the command will be stored in the library cache, such that whenever other users are trying to issue the same statement, instead of performing the syntax check and semantics check, it will use the compiled version which is present in the library cache. So it will actually reduce the time to perform a syntax and semantic check. So once the compiled version of the command is present in the library cache, if the subsequent access use the same code, then it will use the compiled version which is already present in the library cache. So library cache is nothing but it will store the compiled version of the SQL statements. Then coming to the dictionary cache. So once you issue this statement, first it has to check whether EMP table is present in the database or not. And then after that, it also needs to check whether this particular user has access to the EMP table or not. By default, all the users will not have access to all the objects in the database. So it provides a kind of security where all the users cannot access all the objects. So depending upon the privileges they have, they can access the objects. So whenever the user issues this statement, first it will check whether the EMP table is present or not. And also it will check whether the user has access to this object or not. So in order to check whether the EMP table is present or not, for the first time whenever the EMP table is being accessed, it has to go to that physical location and then it has to get that EMP table back into the buffer cache, correct? At the same time, it will also store the physical address where the EMP table is present in the physical storage. That address will be updated in the dictionary cache. So dictionary cache will hold the address where the EMP table resides. And not only that, it will also store what are the users who have access to the EMP table. So it actually stores the physical storage or the physical location of the objects as well as the privilege information. And that is the reason why it is actually called as a dictionary cache, because it holds the physical address where the object resides. So for example, now the EMP table is present in the database buffer cache. That is fine. After that, whatever the 300 MB of space which is allocated for the database buffer cache is used. So say for example, you accessed EMP table, department, and couple of other tables, and the 4 tables consumes the 300 MB of space in the database buffer cache. Now if you access 5th object, first the dedicated server process needs to access the table from the physical storage and then it needs to be placed into the database buffer cache. When server process is trying to place it in the database buffer cache, it will not have any free buffers left because the 300 MB is in use. So whenever server process doesn't find any free buffer in the buffer cache, there is another background process which is called as a DBWR. DBWR is a background process which will flush the dirty buffers from buffer cache to the physical files. So once it flushes the dirty buffers from buffer cache, the free buffers will be present in the database buffer cache, and those free buffers will be used for the fifth table. Okay, once the fifth table is accessed and it is stored into the buffer cache, now other user comes in and again tries to access EMP table. Now the EMP table is not present in this buffer cache because EMP table has been flushed back to the physical storage. For the second time, when the EMP table is being accessed again and when it is not present in the buffer cache, instead of searching the whole physical storage, first it will get the physical address from the shade pool, and also it will check whether the user has privileges or not. After that, it will go into the physical location and it will access the object. So even though the object is not present in the buffer cache, as the shade pool hold the physical address where the object resides, as a result, the data retrieval will be a little bit faster when compared to not having the address in the shade pool, because it has to search the whole location in order to get that object. Do you have any questions till now? Hello? Okay. So inside the physical storage, one type of file is called as a data file, and this data file will actually hold the data corresponding to the database. Now, and as I said, after listener authenticating the user, it will establish a connection between the user and the SCA. So this is called as a connection. To establish the connection, listener is required. Once the connection is established, even though the listener is not running, we can still submit the queries to the dedicated server process. And the information from data files to the buffer cache will be placed by server process, the dedicated server process. So dedicated server process is the actual process which will get the data from physical files and place it into the buffer cache. Now, whenever there is no free space left in the buffer cache, the dirty buffers will be flushed from the memory to the physical files, and that flush will be done by DBWR, which is database writer. But which dirty buffers it will actually flush? So it will uses an algorithm called as LRU algorithm. which is called as a least recently used algorithm. So it actually uses a stack. So whenever, for example, first EMP table is accessed and it is stored into the buffer cache. At the same time, this list, it's actually a linked list representation, and this linked list representation will have two ends. One is called as most recently used end, and another end is called as least recently used end. Now, when EMP table is accessed for the first time, it is the most recently used object. So it will be present at this end of the list, in most recently used end of the list. Now, this is EMP, for example. After that, department table is accessed. Now, this EMP table will go down and department table will be in the most recently used. After that, if you access another table called as salary, now salary will be in the most recently end, and then the department, after that EMP. At this moment of time, if there is no free space left in the buffer cache, it will actually flush the dirty buffers corresponding to the EMP table. So whenever dbwr tries to flush the dirty buffers from the buffer cache to the data files, it actually flushes the dirty buffers corresponding to the object which is present in the least recently used end. Because if it tries to flush the most recently used object, it may be used again by the users. So as a result, again it needs to go to the physical location, again it has to put it back into the buffer cache. Now, the similar thing, first EMP table is accessed, then department, and then sal. After that, again if the EMP table is accessed, then EMP table will move into the most recently used end, after that sal, after that department. So depending upon how the when the objects are accessed, the objects will move between most recently used end and least recently used end, and the objects which are present at the end of the least recently used list, those objects will be the candidates for the dbwr to flush the dirty buffers from buffer cache to the data files. Okay, so dbwr uses LRU algorithm to write the dirty buffers from buffer cache to the data files. Clear?
Yeah.
Now we'll see about redo log buffer, log buffer. Now, as I said, the dirty buffers will not be written back to the data files until server process doesn't find any free buffers on the buffer cache, correct? Now, till now, dbwr has not written the dirty buffers from the buffer cache to the data files yet. At this moment of time, if something happens and power goes off, whatever the content which is present in the memory will be flushed. So once the server comes up, the content in the memory will not be there, as it's a volatile memory, correct or not? So that means whatever the user performed, like whatever the DML statements the user has issued, updates or inserts or deletes, those changes are present in the memory itself. Those are not written back to the data files yet. So how do Oracle require all those objects? So how do Oracle replay all those DML statements in order to store the committed transactions to the data files? So that means like whenever user is performing any DML statements, whenever he issues commit statement, that means the data needs to be present in the data files all the time because it's a committed information.
Yes.
So it actually each and every RDBMS software will follow ACID properties. So the first A stands for atomicity. That means whenever you issue this commit, it should be present, whatever it may be, whatever it may be. Like even if power goes off, if anything happens, if anything happens to the database, even in that case, it needs to get back all the committed data. So in order to replay all these transactions, so whenever the user performs any DML statements, actually a vector representation will be there for each and every statement. As I said, the statement will be converted into a relational algebraic expression. So that relational algebraic expression will actually have a vector representation, and that vector representation will be stored in this log buffer. So whenever the user is performing insert, then information about this insert statement will be present in the log buffer. And usually this log buffer will be of very small size. It will be ranging from 4 MB to 10 MB at max. And if the DML statement you're being performed is of 10 MB, it will not store the entire 10 MB in the log buffer. It will just have a vector representation which can be converted into the actual DML statement which was performed by the user, and that vector representation will be logged into the log buffer, and that is called as a transaction log information. Now, as this is very small, 4 MB or 10 MB, for every 3 seconds the log transaction or the transaction log information from the log buffer will be written into the physical files. There are another physical files, another set of physical files in Oracle database. Those are called as redo log files. For every 3 seconds, the content from the log buffer will be written back to this physical file, which are redo log files, and that will be performed by a background process called as LGWR, log writer. So log writer is a background process which will actually write the redo log buffer content from the memory to the physical files for every 3 seconds. So as a result, whenever power goes off and whenever you bring up the database again, and the DML statements which are issued by the users will be stored in the physical files which are called as redo log files. So using the content which is present in the redo log files, Oracle will replay all the transactions such that the committed information will be written back to the data files. So that is the reason why we'll use a log buffer in order to recover from the transactions whenever power failure occurs. And for every 3 seconds, log writer process will write the content from log buffer to the redo log files. The redo log files will have the information or will hold the information about transactions, whether it is a committed or uncommitted. Whenever the user is performing an insert statement, it will not wait to log an entry into the log buffer until the user issues commit. Whether it is a committed transaction or an uncommitted transaction, the log buffer will hold the information regarding the transaction. And also, once the user issues commit, it will also update the log buffer with, okay, this transaction is a committed transaction. And if the user rollbacks the transaction, then it says it is not a committed transaction. In using that information, it will replay all the committed transactions after the server comes up. Using that information, it will replay all the committed transactions. As a result, the data files will be accurate. The data which is present in the data files will be accurate. So the process which will perform or which will replay all the transactions in case of power failure, or the process which will replay all the transactions after the power failure, is the SMON process. This process is called as SMON, and the full form of it is server monitor. And this is a process which will replay all the transactions. So this process will pick the redo information which is present in the redo log files. Log file 1, log file 2, and this SMON process will pick or will fetch the information from the log files, and it will replay all the transactions against the data files. You may ask, like, instead of having the content in the log buffer and flushing the content from the log buffer to another set of physical files which are redo log files, why can't we flush the redo information back to the data files itself? Why we need another set of physical files? We can have the content from the log buffer being flushed into the data files itself. But the reason for that is the data files will be bigger in size. It may be of 100 GB or 200 GB. And the log information, the transaction information which is stored in the redo log buffer may correspond to the blocks which are present in this 200 GB of this data file. Now, in order to store this log information into the data file, which is of 200 GB, will take a lot of time. It needs to find the free space, and then it needs to find the address, and then it needs to store the redo log information. So it will take a lot of time. Instead of that, it will store it into a smaller file. The log file will be maybe 100 MB or 200 MB. It will be small size. And also these log files will be stored in a storage where the write operations will be faster. So the disks which are used for these log files will use the disks for these log files in such a way that the write operations to the disk will be faster when compared to the disks which are used for the data files. So we'll use a little bit expensive disks to store the log files. As a result, the write operations will be faster whenever the log writer performs, or whenever the log writer takes the content from log buffer and write back to the redo log files. So that is the reason why Oracle uses another set of physical files in order to store the transaction log information. The components which we saw till now are the mandatory components of the SGA. The shade pool, database buffer cache, and log buffer. These are mandatory components of the SGA. There are also some optional components which are present in the SGA. Those are Java pool, large pool, and streams pool. So whenever your front-end applications are Java based, even in the database, you can store Java objects like Java classes. And whenever you are accessing those Java objects, it will be stored in this memory component. So Java pool will be used to store or to hold the components which are related to the Java. So whenever you have Java classes which are stored in the database, and whenever the user is referencing those Java objects, those objects will be stored in the Java pool. And the reason why it is called optional component is because it is used only when you have the front end with Java applications. Next, coming to the large pool, this will be used whenever you're performing any backup operations. So as a DBA, the main task for you will be to provide the high availability of the database. So in case of any failures, you should be in a position to recover the database. So for that, you will take the backups very frequently. And whenever you're taking the backups, this memory component will be used. Large pool will be used whenever you're performing any backup operations. So once you're done with the backup, you don't require this large pool component. That is the reason why it is called as an optional again. And again, there is another optional component which is called as a streams pool. So in Oracle, there is a technology called as Oracle Streams. So these streams will be used whenever you have two databases. One is called as source and another is called as target. Now on this source database, you may have 300 objects. And out of these 300 objects, there are 5 objects which are also required in another database which is called as a target database. So even the users who are accessing this target database requires these 5 objects in addition to the objects which are present in the target database. Now whatever the changes which are present or which are occurred on the objects, on these 5 objects which are present in the source database, need to be replicated back to the target database too, because these objects are being referenced in the target database also. So this replication can be achieved using Oracle Streams. And whenever you configure the databases to use the Oracle Streams, then the information regarding this replication will be stored in the Streams pool component. So this will be used only when you configure Oracle Streams. If you don't configure Oracle Streams, you don't require the Streams pool. Okay.
Okay.
Next, this database buffer cache will actually be of two types. One is default buffer cache. One is default buffer cache and the second one is db underscore nk underscore cache underscore size. So database buffer cache can be of two types. One is default buffer cache and the other one is db underscore nk underscore cache underscore size. So these are the two types of buffer cache. Now, as I said, the buffers in the database buffer cache will be equal to the database block size. That is called as a default buffer cache. Whenever the buffer size is equal to the database block size, that buffer cache is called as default buffer cache. Now there is another set of cache which is called as db underscore nk underscore cache underscore size. Now in the physical storage you will have the data files, and these data files which you create will be I mean, like, for example, if you're creating a data file of 200 GB, this 200 GB will be divided into 8K block size because our database block size is 8 KB. You can also have another type of data file with a different block size. So if you want to create a data file with a different block size, now say 16 KB, that means this 200 GB of space will be divided into 16 KB chunks, 16 KB blocks. So in order to store this 16 KB block, so whenever the server process fetches the information from the physical storage and it will place into the buffer cache, it actually requires the same size of buffer on the buffer cache component. Now if you have a data file with a different block size, say 16 KB, then you also require a buffer with the size of 16 KB. By default, whenever the SG is allocated, whenever the buffer cache is allocated in the SGA component, it will be equal to the database block size. Now if you want to store this 16 KB data files also into the memory, then you need to configure another parameter, db underscore nk underscore cache. So if you create 16 KB block size, if you create a data file with a 16 KB block size, then you need to configure db underscore 16k underscore cache component. Or else if you create a data file with a different block size, say 4 KB, then you require db underscore 4k underscore cache component. So depending upon the block size, you will need to configure this n. So if your block size is 32 KB, then you need to configure db underscore 32k. So even this will be an optional. This will be used whenever you have a data files with a different block size. And I'll tell you, I mean, like, in detail what is a block and which block size we'll be using, and depending upon how the database will be used, how the applications, what applications are stored in the database, we will determine the block size.
When we will create this database, buffer cache blocks, Mohan, like while creating the database or while planning the database?
No, the configuring of db underscore nk cache?
Yeah.
No, you can configure it at any time.
Okay.
You can modify these sizes like this because this is a dynamic component, right? This is present in the memory.
Okay.
So whenever you want to modify each and every component, you can modify it.
Okay.
And how much of SGA will be allocated and how each component will be allocated, we'll see it in the future classes.
Okay.
Next, say for example user is connected to the database and he issued a transaction or he issued a query. Update. After the update statement, he also issued commit statement. Done. After that, he is idle. He is not doing any operations. Now, so say for example he is sitting idle for 2 hours. Still the server process associated with this client will exist on the server, correct? That means it will consume memory and it will also consume some CPU. As it is running in the memory, it will consume some CPU. Even though the user is sitting idle, the server process will consume the resources on the server. So there is a background process which will monitor whether the user is idle or not. So if the user is idle for so many of seconds or so many of minutes, then it will clean up those user process. That means it will first disconnect the user from the database. It will clear the connection and also it will clear the server process. So all that will be done by PMON. PMON will clean up idle process as well as it will clean dead process. Dead process is nothing but if power goes on the client side. That means he actually lost the connection, but still the server process associated with this connection will exist on the server. So PMON will continuously monitor for those dead process and it will try to clean up those dead process. That means it will kill the server process which is running on the server. And also, for example, if user is trying to update, when the power goes off, the user is trying to update, it actually holds a lock on the table. So it also needs to release that lock. So PMON will take care of all the cleanup process. And PMON, SMON, DBWR, LGWR are called as background process. And there are another two background process which are called as MMAN and MMON. Sorry, MMAN and MMON. MMAN is memory manager. What it actually does is the total SGA size is 500 MB. And within this 500 MB, each of component will have, say for example, database buffer cache with 300 MB, 150 MB, 5 MB, and rest of the MB is allocated for the optional components. Now, if database buffer cache is heavily used, then it will reduce the size of shade pool to 100 MB and then it will allocate the 50 MB from shade pool to database buffer cache. So that will be done by MN. Depending upon the each and every component usage in the SGA, it will try to allocate or deallocate more space into each and every component of the SGA. That will be taken care by MN, which is called as memory manager. It will automatically manage each and every component of the SGA depending upon its use. Then the another process is called as MON. MON will actually collect the statistics. How much of CPU is being used, how many processors are existing on the database, how many users are connected to the database, what are the SQLs which are being fired on the database, what are the heavy resource consuming SQLs. So information about all the statistical information will be collected by MON process. So using this statistical information, you can determine like if there are any performance issues on the database. Using this statistical information, you'll determine what caused the performance degradation. And apart from this background process, we already saw server process, dedicated server process, which will serve the actual requests submitted by the clients. All this process will exist on the server side and the client process will exist on the user side. Any questions till now?
No more.
No, Mohan. Yeah, good.
Okay, then I'll wind up the class and I'll continue on Tuesday.
Okay, Mohan.
And okay,
Okay.
and wait, Girish, Ashish, and Siva. I'll give you a Siva's also. I'll give you a conference number. You need to dial into that number.
Okay.
Yeah, 1 second.
Hmm?
Did you note down the conference information?
Yeah, yeah.
You need to dial into that number and then you need to enter the password.
Okay.
Girish, you
Mohan,
got
ఒక
it?
మళ్ళీ రా.
చాట్లో పింగ్ చేసిన కదా ఓకే మళ్ళీ ping.
ఓకే ఓకే సరే సరే చూసిన
Yeah.
చూసిన
గిరీష్
థ్యాంక్
గిరీష్ there?